This is the notes page for properties of logarithms from Unit 3, so we will start with a review. This is the third time we've talked about a log function. So a log function, this is a log form, this is exponential form. Exponential functions and log functions are inverses. So if we have a base b to the y power equals x, you can rewrite that as log base b of x equals the exponent y. So that's a log function. There are a couple of restrictions. B cannot be 1, and x has to be greater than 0. A log is an exponent, so this is a log function. Whatever's in that spot has to be greater than 0. Okay, so we always have to remember how to go from log form to exponential form. Alright, so this is just a little practice here. So remember, to go from log form, log base 3 of 5 equals x, the base is 3, the exponent is x, and it equals 5. To go from exponential form to log form, log base 2, it's a little subscript there, of 32 is 5. So here, log form would be base 5 to the exponent 3 is equal to 5 cubed. Here, the log base 2 of 1/16 is equal to -4. And here, 16 is your base, 1/2 is the power, it equals 4. So that's review. Okay, so now we get into some properties of logs that are really quick, but you always have to remember these. So first one, the log base b of 1 is equal to 0. Because, let's say we log base b of 1 equals something. Let's say we do that. Then we rewrite it in exponential form, that's b to the x equals 1, where there's only one number that's going to make the base b turn to 1, and that's 0. Alright, log base b of b is 1. Okay, so if we wanted to check that out, the log base b of b equals something, right? So then if we rewrite that in exponential form, that's b to the x equals b, and b has an understood exponent of 1. So if we drop the bases, x does indeed equal 1. That's actually a specific property. This is the generalized form. The log base b of b to the x, if you can get the same base here and here, that just equals x. So that's a really important property. I'll go through the y again. The log base b of b to the x equals something. We got to use a different variable, y. So if we rewrite that in exponential form, that's b to the y equals b to the x, and sure enough, x equals y. So you want to try to get the same base here and here. Okay, so for example, the log base 2 of 4. Well, that 4 can be rewritten as 2 to the 2. So if you can get the same base here and here, the log base 2 of 2 to the 2 is just 2, and you do have to simplify that. And then this last one is similar. If you have the base b here to a power of a log base b of x, that also just equals x. And I won't go through that reasoning there because you'd have to take the log of both sides. Alright, so here's some to try. What is the log base 5 of 5 to the 7? That's 7. What is the log base 6 of 1? That is 0. So anytime you have a 1 in that spot, it's going to equal 0. What is the log base 3 of 3? Well, that's like number 1. If we put an understood exponent 1 there, that's 1. And then here, 5 to the log base 5 of 125. They cancel, so that's 125. Alright, common logs, again, this is review. A common log is a log with base 10, so if you don't see a base here, it's 10. And we can use this property here a lot. Log base b of b to the x is equal to x. We've done it before, but now it's official. So the log base 10 of 100 is the same as the log base 10 of 10 squared, and that's just 2 because you got the 10 here and the 10 there to match up. The log of 1,000, log base 10 of 1,000 is log base 10 of 10 cubed, and that's just 3. You can even do it for this using negative exponents. The log base 10 of 1/10 is the same thing as a log base 10 of 10 to the negative 1. You put that 10 in the numerator and use a negative exponent, and that's negative 1. And then still more review. The natural log is a log that has a base e. So if you see an ln, it has a base e. Okay, so this leads us to a really important property. The natural log of e is 1 because of this property right here again. Because you have the base e and 1, and you have the same base here and here, that just is 1. So the natural log of e equals 1. It's a big property. Okay, so now we can use the properties of logs to evaluate the following. So we want to try to use those properties that I just told you about, especially this one. You want to try to get the same base here and here. This is the best property. So if you see, this is hard to teach because some of you don't know your perfect squares or your perfect cubes, but if you see a 36 and a base 6, you should go, oh, that's rewritten as log base 6 of 6 to the negative 2. I can bring that 36 to the numerator with a negative exponent, and so that's negative 2. Okay, don't forget your order of operations are always in play, so you have to take care of the exponent before you multiply. PEMDAS can't multiply before exponent. E comes before m. So this would be 5 times, and then this property here, 4 to the log base 4 of 8 is 8, so that means 5 times 8 is 40. Here, same thing. You have to figure out what the log base 10 of 10 to the 1 is. That's 1, so 38 times 1 is 38. 23 times the log of 1. Remember what any log with a 1 in that spot is 0. So this is 23 times 0, which is 0. And then the natural log of e, remember that's 1, so this is 4.3 times 1, 4.3. So this property especially is a big deal. The log base b of b to the x is equal to x. We're going to add that property to some more properties. They're called the laws of logarithms, or rules, or properties. It means the same thing. Okay, so the first one, and it's good to give them names so we can discuss what's going on, says that if you have a 1 log base b with a product in here, x times y, it's called a product, it's equal to 2 logs added, the log base b of x plus the log base b of y. Okay, this is called the product rule, and it works backwards and forwards. Product rule, or law, product law for logarithms. And what I say to myself to try to remember it is not good math. It's just what I say. 1 log multiplied, 1 log with these numbers in here multiplied, is 2 logs added. 1 log multiplied is 2 logs added, because the rule isn't this. You can't split that up. That is simplified. It's 1 log multiplied is 2 logs added. Okay, so you might be given log base 2 of 3x, and the rules at the beginning of this lesson might just say expand, and that just means use the properties until you can't use them anymore. And it's just skill work. So if I have log base 2 of 3x and I want to expand that, I can say, oh, well, that's the product rule. I have a product. 1 log multiplied is equal to 2 logs with these numbers here. log base 2 of 3 plus the log base 2 of x. And you can go the other way. Here I have 2 logs added. Well, that's equal to 1 log with these two things multiplied. And that looks funny with that 4 on the other side. So of course that's the log base 3 of 4 times x plus 2. And if you wanted to multiply that out, you could. That's the log base 3 of 4x plus 8. And can you split that up? No, you don't split up 1 log added. This is stuck together like glue. You can only split it up if it's a product in there. 1 log multiplied is 2 logs added. Okay, rule 2. If you have 1 log and you have a quotient in here, 1 log with a division, that's 2 logs with subtraction. And that's called the quotient rule. So again, we might say expand. So this would be the log base 4 of 3x minus the log base 4 of 4. So 1 log with a quotient is 2 logs subtracted. Now in this example I want to show you that you have to keep going. So this has got extra stuff in it. You notice here that this is 1 log with a product. So you can use the product rule here. Log base 4 of 3 plus log base 4 of x. Also, you got to keep going with it. When the directions are expand, that means just keep using your log rules until you can't use any more. What is the log base 4 of 4 to the 1? Yeah, same base here and here. Keep your eye out for that. That's just 1. So that's your final answer. You can't expand any more than that. Okay, next one we might say simplify into 1 log. So natural log of 15 minus natural log of 3, that's 2 logs subtracted. Well, you can use the quotient rule and write that as 1 log with division. And the positive one always goes on the top. And then that simplifies to the natural log of 5. Alright, third rule of these 3 big ones is this one. The log base b of x to the p is equal to p times the log base b of x. This is called the power rule for logs. And the power rule for logs says if you have like the log base 3 of x squared, you can actually put that 2 in the front to make it 2 times the log base 3 of x. And that is the key to solving exponential equations, the power rule. You can take an exponent that's on that number and put it in the front as a multiply it. And you can go the other way. If you have 1/3 times the log base 2 of 8, that's equal to the log base 2 of 8 to the 1/3 power. Now this is a tricky one because it actually simplifies more. This is where it gets hard for students. It's hard to teach this because you kind of have to have number sense. See, 8 is a power of 2, right? So, and you have to keep going. You got to simplify. So log base 2, 8 I'm going to rewrite as 2 cubed. So that's still 8. Alright, and then we have this rule here. We have an exponent to another exponent. You multiply those exponents together. So that's the log base 2 of 2 to the 1. Because 1/3 times 3 is 1. And then of course that's just 1. So I power rule here, but then I'm practicing. You've got to know your perfect squares and your perfect cubes. You want to be on the lookout for the same base because that rule keeps tending to pop up, that rule right there. So those are your 4 really important rules. The product rule, 1 log multiplies, 2 logs added. Quotient rule, 1 log divided is 2 logs subtracted. The power rule, you can move that power on the number to the front and multiply. And log base b of b of the x equals x. Okay, this change of base rule has lost its significance because of these calculators we have, but it says that if you have the log base b of n, that's equivalent to the log base x of n divided by the log base x of b. Now that looks really hard to understand, so what we usually use is the common log. Alright, so the log base b of n is the same as the log of n over the log of b. So you can use whatever number you want, so might as well use the common log. Or you could use the natural log. The log base b of n is equal to the natural log of n over the natural log of b. And that came in handy. The calculator used to only have the ability to do common logs or natural logs, but now it can do any log. So if we wanted to use the change of base rule, that would be the log of 5 divided by the log of 3. But I can show you. So log base 3 of 5, if you hit this LOG button once, you get ln. If you hit it twice, you get log base 10. But if you hit it a third time, it allows you to put whatever base you want in. So you can actually figure out what the log base 3 of 5 is. Okay, or you can use the change of base rule. Log of 5 divided by log of 3 comes out to be the same thing. Or you can use the change of base rule with natural logs. Comes out to be the same thing. And we usually round to about 4 decimal places. So 1.4649, but the 9 is going to go up to 0, so that's actually going to round to 1.4650. Some common mistakes. Log of 6 divided by the log of 2 is not log of 3. You cannot divide 6 by 2. Now, the log of 6 divided by the log of 2, if we remember the change base rule, is the log base 2 of 6. I've mentioned this one. Sometimes people will want to split a log that's being added with the numbers added into 2 logs being added. That makes no sense. 1 log multiplied is 2 logs added. 1 log added is not equal to 2 logs added. That's not right. You also can't go the other way. So that's as simple as you can get it. That's simplified. Can't pull apart a sum ever. This one is kind of an obscure one. You don't usually see it, but notice the parentheses. So what this is saying, you can't use the power rule. This 2 does not belong to this x. This 2 belongs to the whole thing. So this is saying log base b of x times log base b of x, which isn't the same thing as 2 times log base b of x. Okay, so you have some really good practice problems in the lab manual, but let's practice a few with the directions. So this says simplify this log. Okay, so I've got to take a minute to say we can't use radicals. We have to use exponents. So we have to remember this rule here. The nth root of x to the n is equal to x to the n over m. So you have to use rational exponents. Okay, so first thing we do before we can expand this is we have to rewrite this as the log, it's base 10, of x squared plus 5. Now this is difficult. This whole thing is being raised to the 1/5 power. So there's an understood 1, and then that 5 is the index. So the only rule we can use here is the power rule. We can take that 1/5 and put it in the front. But we can't split apart the x squared plus 5. That's a no-no. If you have addition inside this spot right here, it's going to be, you're stuck with it. Okay, you can only split it apart if there's a product in there. So there's not much to that one, but I did want to take time to tell you that you've got to get rid of all the radicals and use rational exponents to do work with logs. Alright, the next example, simplify. That means, so you have 3 logs added and you want to try to get it down as simple as you can, maybe 1 log. So the first thing I see is, before I can do anything else, I'm going to use the power rule. So I can take that 7 that's in the front and make it an exponent with the c. Can you do the same thing with the next one? Yep, that would be log base 5 of a to the 1/8. Can you do the same thing with the next one? Yep, that would be log base 5 of b to the 1/8. So now we've used the power rule. Okay, now we have 3 logs added, but they have the same base. So can we combine that into one log? Logs added together can be written as one log with the numbers here multiplied together. This is the product rule going the other way. Okay, and then just to practice this, you could go further. You could say, well, this is, they both have the same exponent, so this is ab to the 1/8 power. And then that is the 8th root of ab. Yeah, just to practice rational exponents one more time, but you could stop right here. I would accept that. Okay, so in the lab manual, it's currently page 127. That might change, but it's laws of logarithms. So look at the table of contents, and you've got the product rule. 1 log multiplied, 2 logs added, or 2 logs added can be written as 1 log with those numbers multiplied. Quotient rule, power rule. Okay, and we have some ones to practice. So I'm not going to go over all of them, but I will go over number 1 and 4. So number 1, just because radicals can be troublesome, remember you have to rewrite that using rational exponents. So that's going to be the log base 2 of 8a cubed to the 1/2 power. And so I also want to go over exponent rules. We've gone over this one. We've been using this, so hopefully you haven't been lost. When you want to multiply 2 powers together, you same base, you take the x and then you add the exponents, right? And when you want to divide, you subtract. All right, well, when you have x to the m to the p, you multiply those. So we know that. And then if you have x to the m, y to the n to the p, that p goes to both of those exponents. So these are exponent rules that you hopefully saw in high school. All right, so that's what I want to use here. So this 1/2 doesn't just belong to the a cubed, it belongs to the 8 and the a cubed, because if you have a product in here, you're basically distributing that exponent to both of those. So I'm going to write that. That's a log base 2 of 8 to the 1/2 times a to the 3/2. Because 3 times 1/2, 3 over 1 times 1 over 2 is 3/2. Okay, now we want to expand. So 1 log with this product is equal to 2 logs added. So we'll split this up. So this is a hard one. Okay, now notice that this 8 is a base 2. So I'm going to take time to write 8 as 2 cubed, and it's being raised to the 1/2. 8 is 2 cubed. While I can do it, let's use the power rule. So we'll take that exponent, move it to the front. You got to keep using the rules until you can't use them anymore. So now, again, exponents, I can multiply those together. That's the log base 2 of 2 to the 3/2 plus 3/2 times log base 2 of a. And then we have that rule that I said is going to keep popping up. Log base b of b of the x is x. Log base 2 of 2 to 3/2 is 3/2. So we have used every rule we can use to get this. Okay, so try that one again later. just copy it down and see if you can follow along. And you can do things at different times. So this has to be the first step. You have to use rational exponents. So that 1/2 came from the fact that 8a cubed together has an exponent of 1 and the index is 2. So that's where that came from. And then I used this rule and gave both of those the pieces of the product, the 1/2. And then that was when I used the product rule. It also helps if you practice, if you write out what you're doing, if you think about what you're doing. And then I decided to use the power rule there. Alright, and then I multiplied those together, and then I used this same base rule there and got that. Alright, the other one that I wanted to do with you is because I have an extra rule for you. It's kind of a combination of the quotient and product rule. And it's a lot easier to think of it this way. If you have a bunch of products and quotients, see there's a quotient and there is a product. The product rule says 1 log multiplied is 2 logs added. The quotient rule says 1 log divided is 2 logs subtracted. Well, you can put the whole thing together and do it this way. If you know that, so everything's going to be addition and subtraction. All you have to remember is that the numbers in the numerator get split apart and they're going to be positive, and the numbers in the denominator are going to be negative. So this is a combo product quotient rule. This would be the log base 3 of 9 plus the log base 3 of x to the 5th. This is in the bottom, so minus log base 3 of y minus log base 3 of z to the 4th. Okay, and now we can go further. 9 is 3 squared, isn't it? And then we can use the power rule here, so that's 5 log base 3 of x. And then use the power rule on the last one, that's 4 log base 3 of z. And then finally, the log base 3 of 3 squared is just 2. We lose the log because of that great rule. Same base rule here and here. Okay, so to finish up, I'll show you why that works. So if we did this the long way, you see a quotient, right? So that would be the log base 3 of the numerator, 9x to the 5th, minus the log base 3 of the denominator, yz to the 4th. That's the quotient rule. But then we have to split that up using the product rule. So that's the log base 3 of 9 plus the log base 3 of x to the 5th. Now here's where it gets tricky. This is the product rule. But see that minus? It's the same issue that we have with minus all the time. If we split this into the product rule, it's going to become 2 logs. Well, who does that minus belong to? It's going to have to belong to both of them. You got to use parentheses. So minus, now we'll use the product rule, plus. And then we're going to have to distribute the negative, and that's why that works. So the product and if you have a quotient with a product in the numerator and denominator, you can kind of combine it all into pluses and minuses. Just remember that the pot pluses come from the numerator, and the minuses, because they were the denominator, the quotient rule, that minus is going to end up belonging to every one of those terms. So that's the combo product quotient rule. This page you're going to be rewriting each as a single logarithm. So this, you'd have to use the power rule first and then the quotient rule, and so forth and so on. And then this last page is a great test of really understanding the properties. You have to tell whether these are true or false. And it says make the for each false statement change the right side. You don't have to change the right side. You can change the left side if you want. It doesn't matter to me. But what you want to do is you want to make sure that this side equals that side. If it doesn't, then you have to fix it. Fix one of the sides. So is it true that the log base a of 3a squared equals 2 plus log base a of 3? Well, let's figure it out. Let's just expand the left side. Try not to look at both sides at the same time. So I'm using the product rule here. And then the log base a of 3 you can't do anything with, but the log base a of a squared is indeed 2. So is it true that the log base a of 3 plus 2 equals 2 plus the log base a of 3? Yes, it is. Okay, so just pick a side and use your properties and then see if that does indeed equal the right side or the left side. I don't care which side you think you want to work with first. So that's a little change to the directions.